Well, I'm going to talk today about the Rangeland hydrology erosion model. I'm just going to provide an overview. It's better? Okay. I'm going to talk today about the Rangeland hydrology and erosion model. I'm just going to provide an overview of the model and kind of set up the stage for other speakers that actually they are using the model for a very specific applications. This is a team effort, and so I didn't want to put names there because I don't want to miss any person, but I want to acknowledge the groups that has contributed into this project, the Great Basin Rangeland Research Center in Reno, Nevada, the Northwest Watershed Research Center in Boise, Idaho, Southwest Watershed Research Center in Tucson, Arizona, and the NRCS in Fort Worth, Texas. On Monday, I was in a talk, and actually the talk was on a application of ecological sites descriptions to management of Great Basin rangelands, and the last speaker, actually a land manager, she had a one-slide presentation, but her take-home message was that land managers, they don't embrace the models because they are difficult to use, difficult to interpret, and very expensive to run the models. My take-home message, I hope that by the end of this presentation and at the end of the several series of talks in this session will be that convince land managers that we have developed a tool, a very simple tool that we capture very complex processes and put it in a very simple web interface that can be used for land managers to make decision management practices. So just as a background, a great deal of work has been undertaken to develop soil erosion models, and the focus has been on croplands applications. For example, in the process of developing the USLE equation, 49 research stations were placed around the country, and none of them were in rangeland site. So that tells you that the emphasis, the priorities at that time was for cropland research. Therefore, there is a need for a soil erosion process-based model that will allow us to predict, assess runoff and soil erosion rates on rangeland. And here, that's what we have achieved as far as when we designed this model was designed specifically for government agencies, land managers and conservationists who need sound science-based technology to assess, model and predict runoff and erosion rates on rangelands and to assist in evaluating rangeland conservation practices effects. I want to point out that this project was funded mainly by the CEAP project, Conservation Effects Assessment Project, NRCS. How this model came about. This is based on the web project, Rainfall simulator runs that were conducted around the country on these 15 western states, and they were run on 204 plots. And the idea was to run a pair of plots, a 10 by 3 meter, with this boom rainfall simulator, and collect data at the bottom of the plot, runoff and soil loss rates, concentrations, sediment concentration, and also map out all the vegetation on the plot to then associate parameters affecting the response of the system. I want to also point out here that when we develop our model, we design the model in the sense that we acknowledge that models evolve with time. So we, with new technology, with rainfall simulator, new technology, new sensors, we are able to capture more detail in the landscape. So we want to bring that new knowledge into our models. So the model itself, it's readily capable to adapt that new technology and that understanding. So across this conference, I have heard about scale issues, and I want to set up here the scale of this model. RHEM is basically for computing sediment delivery rates at the spatial of a Hillslope scale. And it's a single rainfall event model. So this is important because when we want to apply the model to a different scales, we want to make sure that the model is applied correctly under these assumptions. However, we have developed a web-based interface, and also we have incorporated the model into this GIS framework if we want to scale up our application. And I want to reiterate again that this is important because the RHEM can capture up-to-date scientific knowledge. When down the road we develop new methods, new parameter estimation equations. So from here I want to basically describe what the model its components. And I want to emphasize that on these modules where we have the user input, the parameter estimation, that's where we capture new knowledge. This is the core engine, basically describing the complex processes, infiltration, overland flow, erosion processes by sheet and splash, and concentrate flow, and also the output. So when we designed the model, we wanted to use readily available data that any land manager can have access. So we will be encouraged to use the model. And also we want a robust model that can that can describe, at least not on with absolute values, but a relative change, that if the user wants to check, for instance, if there is more vegetation, then we may have some less runoff, or that things that processes will match with the reality. So we have the storm characteristics, slope, hill slope characteristics, soil texture, and plant cover, plant foliar cover, and ground cover. We have these major key important parameters: hydraulic conductivity, the Darcy-Weisbach friction factor, splash and sheet, the concentrated flow coefficients. That based on this information, we have developed new equations, and Sam and others will speak about some of these parameters. The engine, well, I'm gonna jump into right now to these storm characteristics. We have two different ways to input storm characteristics into the model. One is actually to use the hyetograph, which is basically a time accumulated depth or time intensity breakpoint pairs. I mean, if you have that information, you can integrate into the model. Or We also have linked the model into this stochastic climate weather generator, climate, which, based on statistics, generates these 4 parameters, and using a disaggregation model based on a double exponential distribution, we get a rainfall intensity pattern that will go into the model. When we run the climate model, we run it for 300 years. So that means that we can compute return periods for runoff and soil loss, and we can actually get average annual values for those variables. As far as the Hillslope characteristics, we need these 3 parameters. Slope steepness, which is just basically the rise run on a percent basis. But something that is really important when we're talking about scale issues, that's the slope length. I just borrowed this figure from this Mayer and Foster. So I want to point out here that the slope length is the length that starts at the top of the hill and goes down to the either where we find concentrated flow or deposition, or we run into the channel. In this model, we don't do any channel routing for sediment. So therefore, that's the definition for slope length. Again, this slope length can be obtained either just go out in the field, or you can extract that information from the national databases, like for instance, Sorgo. Slope shapes, also we can characterize the slope either by uniform slopes, convex, concave, and complex, where you may have deposition here. We also have some features that if you have a survey data along your hill slope, you can actually input those values and then have a very detailed characterization of your hill slope. Soil characteristics. We use the 12 soil classes based on the USDA textural soil triangle. And we are interested at the upper 4 centimeter soil depth. With cover characteristics, we are interested in collecting foliar canopy cover for these life forms, shrubs, bunch grass, saltgrass, and forbs. The reason for selecting these life forms was when we go and analyze the data, web data, we found that the model was sensitive to these life forms. We cannot model every detail on the landscape. So we have to narrow down to these life forms. As far as ground cover component, we do need information about rock, litter, basal area, and cryptogams. So you can see here from this, so far, we need information readily available out there. This is just a schematic diagram that explains the processes that we are dealing with, the way that we represent in the model. So we have rainfall and then overland flow, and we use the Smith-Planch infiltration equation, and then we use the kinematic approximation to route the water along the plain. As far as the soil processes, we account for the, we solve this partial differential equation for sediment concentration, and we take into account the splash and sheet detachment, and also we account for the small concentrated flow areas along the plain. I just want to just go briefly these equations and point out that these are the key parameters that I showed before in that schematic flow diagram. And these parameters are computed based on the information that we collected out in the field. So, so we can update these parameters. Once we have more information, up-to-date information, we can improve our estimates for these parameters that drives the RHEM model. The challenge here was actually mathematically to link these two components. We want the user to run the model, but we wanted to have it within 1 minute up to 2 minutes. So we have to find algorithms that will solve these equations within that time frame. Otherwise, the user will be discouraged to use it, and they may not use it at all, you know. Just briefly mention the formulation based on Bennett concepts, Bulugina contributions. Once we go, these are the equations that we have developed for the effective hydraulic conductivity based on Liter and Basel. We got for one equation for each soil texture class, and this is based on the work by Rawls. Again, once we have more information, we can actually update these equations and do a better performance on the model. Again, with the Darcy-Weisbach friction factor, these equations are based on the data that we collected, based, for instance, Liter, rock, Basel plus cryptogram, and the slope. So, for instance, if we are interested in looking at the sensitivity of the model to the slope, well, definitely here will be incorporated. Again, Sam, he will talk about later, we put his equations into the model. Briefly here, I believe Sam is going to talk a little bit more about these parameters. The paper is in progress, and also the flow detachment. So if you want to know more about the model, I encourage you to go to this link, and then you can, all the documentation is there and the model. Again, every model has to be evaluated in order that we present or that we have credibility in the model. This is Walnut Gulch, our experimental watershed in Tombstone, Arizona, southeastern. And we applied the model at some of the rainfall simulator plots here, but also I was interested in applying the model at the larger scale right here. I used these Lucky Hills 106 small watershed, 0.36 hectares. These are some of the characteristics. Rock 67%, really well protected. Basal 5%, Liter 5%. Soil Lucky Hills McNeil sandy loam, and a canopy cover 25% with a slope of 8%. Based on the rainfall simulator plots, we ran 4 rainfall simulator plots on those in that site that I mentioned, Lucky Hills, but also we ran it on other sites, and you can see, as we expected, good behavior of the model using the rainfall simulator plots. However, when we ran the model at Lucky Hills 106 on that small watershed, runoff is pretty good. I mean, as far as the Nash-Sutcliffe efficiency coefficient, 0.6. But as far as the soil loss, I mean, we find that, I mean, we got a R squared 0.82, but a really low efficiency coefficient of 0.35. Still a positive number, but definitely we see a bias here in our model. Again, we're working, and hopefully we will be able to fix that, correct this bias, and hopefully bring it at least to this level. But this is out of the box. This is no calibration. This is just running the model with the data that we collected out there in the field. Right now, just going to go through this RHEM web interface, and that interface captures all these complex equations and put it down into 7 steps to run the model. We have, first step is to define the scenario. You can just name it whatever you want, reference state, or write a description here. And then we got the climate station, soil texture class, slope, cover characteristics, run the model. And then if you want to do a comparison, then you click this button here. As far as the climate stations, we have all 2,600 client stations, so you can actually run the model across the United States. The reason that we put all these stations, I mean, remember that we are dealing with a rangeland model, but some colleagues requested they want to use it in pasture land over here. So we decided, okay, well, let's put all the weather stations and have them available for the user. Now, if we go back to the soil texture, then this is the windows that you will find when you, well, in a climate station, then you, for instance, in this case, I run the model in Arizona, Tombstone. You will select automatically the station. In the soil texture, we deal with a sandy loam. You will see here this pop window that will provide the 12 soil texture classes. From here, automatically, the model query a database and bring in values that will parameterize the model. As far as the slope characteristics, again, you input the slope length, slope shape, and the slope steepness. Here we have a value, we recommend a value of 300 feet slope length, or 120 meters. Beyond that, experts, they say that its slope length is too large. As far as the cover characteristics, again, we've got foliar cover for bunch grasses, forbs, annuals, shrubs, saltgrass. For ground cover, basal plant cover, rock, litter, and cryptogam. Once you get to this point, you cannot skip this point. You have to follow in a sequential form. Once you get to this point, you just run the model, and it will take about a minute to run it for this Arizona cladding station. If you run it, for instance, back east, it might take at the most 2 minutes to run 300 years. I'm not going to go through these numbers. I just want to present this as a case, how you will see the input summary. So for instance, here I run the model for a state transition model where I have the historic climax potential reference state, and we have an eroded state, a shrub invaded, and exotic grass. So going out in the field or from literature review, I got these parameter values. Again, I created each scenario, run the model for each one, and then from here you can see the input parameters. We allow the user to edit the input parameters file in case that For instance, someone say, okay, well, I disagree with this value because I have expert opinion. The user will be able to edit that part of the input file. This is an output summary. You will have a average annual graphs for each variable: rain, runoff, sediment yield, soil loss, and average annuals for, again, for each of those scenarios. And then because we run the model for 300 years, then we can actually compute the return frequency graphs or return periods for each of these scenarios. So at least this type of analysis convey to the user a simple way to characterize the what's going on out in the field. For instance, in this state transition model example, well, the user can say, okay, well, I may want to treat this state because I got this some amount of soil loss, so I want to apply this type of conservation practice. Model applications. We run the model at the major MLRA 41 in Arizona. We apply the model for 31 ecological sites with NRI data. References right here. Also, we apply applying the model at all 17 western states using 10,000 NRI points. And again, the references right here. Well, I guess I'm not doing anything here. So our colleagues down in Boise, they are doing disturbance. That's something that Sam will talk about. But again, all the information is available in our website, and it's valid. It's something that has been peer reviewed, and we think that the model is robust to characterize at the scale of Hillslope processes, runoff and soil erosion. Again, we use the state transition model, and Jason is going to talk about how he implemented a procedure how to use the RHEM model to assess the states. So he's going to go in detail as far as how to use the RHEM model in that case. Future work, again, once we got more information, either by using more sophisticated systems, rainfall simulators, new sensors, new databases, we can update the model. Well, they want me to. Also, we are updating our interface. We got a comment from users as far as they want to have some features into the interface. We evaluate those concerns, and we decide whether we can change our interface. We are working on a risk assessment where we can actually compute the probability of occurrence of different scenarios. That's on the works, and our commitment to have the final product is at the end of this year. We are incorporating fire scenarios. And also we want to incorporate orographic effects into the weather climate generator. And also we are getting feedback from our colleagues, NRCS, and other users, how to design and how to present, convey this information in a very simple way, just graphics, bar graphs, whatever that makes simple the interpretation of these processes, but also we want also to present and have the other users, researchers, to have access to more data. We can actually map out the soil loss along the hill slope at every time step of the hydrograph. That's a lot of information to convey, but it's available in the model. Thank you. Any questions?